Hello, welcome to our video solution for problem 4 from quiz 3. So we are finally to these line integrals. So these are line integrals of scalar functions. And in this problem, we're not going to go through the full computation. We just want to set up a single variable integral. And remember, the idea here is it's not so hard to get computer programs to compute integrals for us. However, it's a little bit more challenging to get them to compute line integrals, right? Most of them don't really have a nice way of inputting things like, okay, this is the curve, here's the parametrization. It's a little more challenging, but it's fairly straightforward to go to, say, Wolfram and put in a regular single variable integral. So we definitely want to be able to set up line integrals and convert them into something that we can just let the computer do. So let's see here. So here we're given a parameterization for a curve. Looks like it'll be some sort of a line segment, but it doesn't really matter. Let's see, we have a line integral. The function is x plus y plus z, and we want to convert it, into this single variable integral. So typically the way we work these is we're going to work left to right. We start with parametrizing the curve c, and thankfully that was already done for us. And that lets us know that when we integrate, the t is just going to go between 0 and 2. Okay, working further, we want to evaluate this function on the curve, right? All we care about when we compute a line integral is what are the values of the function along this curve. And we know that every point on the curve is given by this parameterization. So the x-coordinate is 1 minus 3t, the y-coordinate 2 plus 4t, and the z-coordinate 5. So I can replace my x with 1 minus 3t, my y with 2 plus 4t, and my z with 5. All right, of course, there's still this ds to take care of, but okay, nice little simplification if we really wanted to. We'd say, okay, let's see, I have a 1, a 2, and a 5, that's an 8. And then I have a minus 3t and a plus 4t, so this will be 8 plus t. Wonderful. Okay, last thing we need to do is convert this ds. Okay, so remember this ds is coming from the arc length of a curve. Okay, and that meant you had some little change in the y and some little change in the x. Of course, this gives you a right triangle, and so we knew the relationship between all these three was given by the Pythagorean theorem, which is great because now you could take the square root and you'll have ds is the square root of dx squared plus dy squared. Okay, and since ds is supposed to represent some sort of a length, we don't have to worry about the minus sign when we take the square root. Okay, and if we also remember that dx is equal to x prime of t dt, and dy is y prime of t dt, which you might believe if you said, oh, well, yeah, what is dx dt? That's the same thing as x prime of t. Okay, then I could replace these dx's and dy's with x prime of t dt and y prime of d dt, respectively. And if I do that, well, the dt is going to show up as a square everywhere, and I can pull it outside the square root. And I end up with x prime of t squared plus y prime of t squared, and the dt is popped out of the square root. Okay, so it's probably a handy formula just to have at the ready, that's for sure, but it's really important to understand where it comes from. All right, so I tend to create it on the fly, even though I know this formula by heart. All right, so what do we do here? We're going to have a square root. I need to take the okay, of course I did this in 2 dimensions, right? We have 3 dimensions here, so when we have 3 dimensions, of course, we're going to want a plus z prime of t, right? Everywhere we could have had a plus dz squared, but that's not a big problem. If you go to 3 dimensions, the Pythagorean theorem still works. And it's not going to change actually our answer whatsoever, because when we take z prime, we're going to get 0 anyway. So in this case, remember, our x is just coming from this parameterization. So when I take the derivative, I just get -3. And then I square it, and I get 9. And now I take the derivative of y of t, and I get 4, square it, and I get 16. And then the derivative of 5 is, well, that's actually 0. So when I square it, I get 0. All right, so that's a 25. Of course, there's a dt out here. So this is the square root of 5. So we've reduced it to just doing 5 times the integral from 0 to 2 of 8 plus t dt, which of course is not hard to compute, but that's not the point of the problem.